Now the term one-to-one function, and you'll see this often brought up from time to time in various rules in calculus, depending on how far you go into it and things like that, because there are certain rules in calculus that only work if you have a function that is one-to-one. And of course, the one-to-one, the two functions we just looked at, for instance, were one-to-one. It's a situation where I have a function whose inverse is also a function. That's what a one-to-one function is. So it has to be a function. Its inverse must also be a function. So sometimes when they say, is this function one-to-one? Well, you can see if it's a function, okay. Is its inverse a function? Okay, but the answer is no, then no, it's not one-to-one. Um, the reason why we bring up a one-to-one function here is that this round-trip theorem only works like establishing if I have one-to-one functions, okay. Right now, when they say use composition or determine whether or not these are possibly inverses of each other, you can kind of just assume they're one to one or being treated as one to one. So any function restriction or any domain or range restrictions that have to be done to make that happen are being done. So all we're looking to see is, can these two in fact be inverses? And again, at face value, I see a square root on one, I see a square on the other. Those are inverses. Those are opposites. I see a +2 and a -2. Those are opposites. So, face value, it's yes. But let's go through the process. And the process of the round-trip theorem says, if I do f of g of x and get x, and do g of f of x and get x, then, and only then, can I say that, these are inverses of each other. And that's what I need to establish. And I do have to make sure I do both. We've already talked about the fact that composition is not necessarily commutative. So it can happen that, f of g of x could equal x, but g of f of x isn't going to equal x. So I do got to test both. So here I'm going to do f of g of x. And when I do f of g of x, I replace g of x with x squared minus 2 because that's what it is. I then go to the function f of x, replace the x with an x squared minus 2, which means that the minus 2 and the plus 2 cancel, leaving me with the square root of x squared, and the square root of x squared is x. So it works there. And g of f of x, first thing I do is I put in what f of x is, which is square root of x plus 2. I then go to the function g, replace the x with the square root of x plus 2, so I end up with that quantity squared minus 2. When I square that square root, they cancel, giving me x plus 2 minus 2, and of course the plus 2 and minus 2 cancel, leaving me with x. So both of these ended up being x. These are inverses. When I look at B, again, face value looks like, okay, well, I see a multiplication of 3, I see a multiplication of 1/3. Well, multiplication of 1/3 is the same thing as dividing 3. Those are opposites. I see a plus 2, I see a minus 2. Those are opposites. So I would have students sometimes incorrectly identify these two things as being inverses. But let's take a look at this. I'm going to do f of g of x, which means the g of x is going to be replaced with the 1/3 x minus 2. I then go to the function f of x, replace its x value with 1/3 x minus 2. And when I carry through the simplification and distribution, I get x minus 6 plus 2, which ends up being x minus 4. Well, x minus 4 is never ever going to equal x. It's always going to be 4 less than whatever x is. I don't have to bother doing g of f of x here because, it has to work for both, and since I found one of them doesn't work, doesn't matter, these are not inverses. So that's how you can use that round-trip theorem in composition to determine whether or not things are inverses. and only tables, because if I had a table but yet I had a formula that produced that table, I should really be looking at the formula and not the table. If all I have is the table, then that's all I have, and I also have to be aware that only having a table of values representing my function is very restrictive, because I'll have students, like for part A, it says, what's the domain of f of x? And you can see that the first table is our f of x function. They would say the interval from -3 to 3, and that's wrong. Because I would have, I mean, as I said, students would sometimes say this. They would say, oh, well, that domain is -3 to 3, because that's what my x values run from. They go from -3 to 3. And you're partially right, but then I have to pose the question to you, well, okay, with that table, tell me what f of -2.5 is. And it's like, well, I don't know what it is, or I would have to take a guess. I'd say, well, it would be like 3.5. Well, how do you know that? Well, you went halfway between your x's, so I went halfway between my y's. Well, does the table say that's what's happening? Does that table really tell you? I mean, how do I know, like, between these dots? And because when I look at that function, it looks like it's doing more along the lines of this. How do I know it's not doing all sorts of cockamamie things between, like this? So how do I know what's happening at -2.5 at all? The fact of the matter is I don't. And because of that, there are undefined values, for this thing. So when I state the domain and I say -3 to 3, I'm saying, well, all x values between -3 and 3. That means like -2.5, -2.9, -2.99. I have a y value that I can evaluate for it. I don't. I don't have it. That's not in the table. So this has to go too. Because all I have is a table and no formula, no graph, anything else that lets me get a better idea of what the function may look like. All I have is a table. All I could do is list them and use my set notation. So that's my domain of f. So again, if all you have is a table, when you list the domain, it has to be individual values. You cannot give an interval, because an interval means that all values between those are also included. Same thing with the range. The range goes from -2 to 4, but it's only those numbers, -2, -1, 0, 1, 2, 3, and 4. I look at the domain and range of G, same kind of thing. Now, at this point, one of the questions that sometimes is asked of students, like at this point, they'll say, well, then, if I look at this, then I mean the domain of f is the same as the range of G, and the domain of G is the same thing as the range of f. Are these things, in fact, inverses? Well, you just don't look at the domains and ranges, because it really the matching up of certain things is going to matter. Okay, so you have to be very careful about that, because if they're not matching up in the same kind of, or similar manners, then no, they're not going to be inverses. I mean, so we're going to look more into that, because when I look at the like for instance, give the table of values for f -1 and give the table of values for g of -1. Pretty straightforward, because again, when I do the inverse of a function, I am switching domains with ranges. So I'm going to take the values for f of x and replace them. I'm putting them in order, typically for the x's. And I'm just matching up the y value, the original x values that went with those y values. So at -2 for the y value, I had an x value of 3. Now that's my new y value. At -1 for my y, I had a 2, so forth and so on. So I'm just switching my x's and y's and making sure to put my x's all in order, and the y's have to still be associated with the original x, or I should say that the new y is associated with the old y, which is what x is. And g -1, same kind of thing. Switching my x's and y's, making sure that I also list my new x's in the right order. That's what I would get. And I'm going to look at these in a moment. I'm going to leave these here because I'm going to do some comparisons that kind of let me know that f of x and g of x are in fact not inverses of each other. But now I have enough information to say, okay, like what's the domain of f -1? And I can see it runs from -2 to 4, again listing the numbers. Very similar to what I did in the first 4 instances when I was looking at f of x and g of x. if I do fog f of g of x, if these were in fact inverses of each other, then I would expect to get, plugging in -3 would get me back -3 when it was done. That would happen for every number I have here. Well, let's have a look and see how we would go about doing this. If I'm doing f of g of x, and first I'm going to start with the innermost function's domain. So that's why you see here, if I can get the right color here, give me a second. I'm starting with g of x's domain, and g of x's domain is this group right here. So that's the first thing. That's how I start off my table. Now, with that being said, we'll get rid of these. If I get the eraser to show up, that's always a good plus, and bam, bam. So basically, if I'm going to do, like, for x being -2, I'm going to start with -2, plug it into g of x. That becomes 0. That 0 becomes the input I'm going to use for f of x. So I plug 0 into the f of x table. I get 1. Therefore, that's what the y value is going to be on my table. For -1, again, I'm going to start at -1 in the g of x table. Let that be the x value, which gives me a y value of -3. That -3 becomes now the x value for f of x, and that produces a 4. So the y value I'm going to have down there is now going to be a 4. For 0, 0 is going to become 1. That 1 is going to become back into a 0. I plug it into the other function, so it's going to be 0. The 1 goes to -2 in g of x. That -2 is then plugged into f of x, and it's going to produce a 3. And so forth and so on. You get the idea of how later we're moving about this, hopefully. So that's my table of values. Now, if they had in fact been inverses, my x and y column should always have the same number. So it'd be -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, 2, 3, 3, 4, 4. That would be an indication that I would have, of two inverses together. Because again, if I compose them, I end up with the x value again. Same thing with g of f of x. And here I'm just going to kind of show it a little bit more shortly. Again, I'm starting with the innermost domain. I'm starting with f of x's domain. That's why I have the x's go from -3 down to 3. And then again, I'm going to follow, start with -3, I'm going to go to 4, then 4 is going to go to 2, that sort of thing. And I'm kind of showing it right here with different colors. So -3 goes to 4, 4 goes to +2, -2 goes to 3, 3 goes to -1, so forth and so on. And I have a nice little rainbow up there. You get the idea. That's how I fill in the table. Again, G and F are not inverse. I mean, when I look at the domains and ranges when I write out the list, oh yeah, the list, because I'll usually write them in numeric order. Yeah, they look like, they're, the domain of one's a range of the other, but it doesn't quite work that way because how they match up is also important with that. Getting back to these, now if I do f of f -1, yeah, if I go through that entire process I just did, so I'm looking at the ones on the left here. If I start with this one's domain, let me get my thing here. Use that color. If I start with this one's domain, that means I'm going to start with these x values here. And so -2 becomes 3, 3 becomes -2, and -1 becomes 2, 2 becomes -1. If I keep working with that, I keep on seeing this. But again, that's what I would expect to happen if I take a function that's inverse and compose them together. Whenever I start with an x value, I should get back that x value after I do the two functions operations together. Same thing for L. So now I just took a shortcut. I said, well, I started with g of x's domain. Make sure that got transferred down here. But as far as me doing the composition, then I should end up with the exact same value as I had for x for my y value. And that's how I got the answers that you see here. And that's all I have to do for this third part. So hopefully now you have enough information to attempt the problems from part 3 of your practice exercises. Then we'll go over those in lecture when we next meet. Until then, have a good day, everybody. And, Next part will be on chapter 2, dealing a lot with quadratics. Have a good day, everybody.